Hello and welcome back to Complex Analysis. And as always, first I want to thank all the nice people that support this channel on Steady, via PayPal or by other means. Now, today in part 3, we continue talking about complex differentiability. More precisely, we introduce the complex derivative and I explain to you why this gives us a linear approximation. And finally, at the end of the video, I show you concrete examples. However, first please recall that the domain of the function we consider is always an open set we call U. Moreover, from this set U, we always fix a point Z0. Now, because the set is open, Z0 is always an inner point. Which means that there are a lot of points around it, such that limits make sense. Indeed, this is what we need when we want to define that the function f is differentiable at the point z0. And if we want to make it clear that we have a complex function here, we say complex differentiable at z0. Now, we have seen in the last video that this definition here looks exactly the same as for real functions, namely that the following limit exists. Indeed, this is the slope of the function at the given point. And often it's called the differentiable quotient. Now, since this describes the slope, we can reformulate this to a linear approximation. The only problem is that the visualization is not so good when we deal with complex numbers. Here I mean that for a real valued function, you can simply draw the graph of the function. So maybe it could look like this. However, for a complex function, the input is the complex plane and the output is the complex plane. Hence, the correct visualization of the graph of the function should live in 4 dimensions. So you see, there's no way I can correctly draw this here. Hence, we just take an abstract picture then, where the x-axis represents the whole complex plane C. And in the same way, the output, the y-axis, also represents the whole complex plane. So you see, we lose a lot of information here. It's not the best picture at all, but we can see the linear approximation then. In other words, we approximate the function f around this point z0 with a linear function. Therefore, you recognize this works exactly as for real-valued functions. So we get a statement that is equivalent to our definition of being differentiable at the point z0. Namely, we just have to give this expression a new name and we call it a function delta. And this delta gets an index where we write the function f and the point z0. Then you see, z could be any point from u, so we have a function from u to c. Okay, and now we can just reformulate this expression here and we get the property the function delta fz0 should have. Namely, f of z can be written as the constant f of z0, so the value at the point z0, plus a linear term times the delta function. Of course, this property here holds for every function f, so we need one more ingredient here. And here, please recall, we want that this limit exists. Hence, this means that the function delta fz0 is continuous at the point z0. Hence, this continuity property is really what we need, and this one makes the differentiability. Now, with this linear part here, you might already see why we call this a linear approximation of the function f. If you have never seen this, you can watch my real analysis course where I talk a lot about linear approximations. However, here we finally should define the derivative of the function f. This is not so complicated because now we have everything. Moreover, you might already know the derivative is denoted with f prime. And then in parentheses we write the point z0. And now by definition, the value of the derivative is simply the output of the delta function we get when we put z0 into it. And now because delta fz0 is a continuous function at the point z0, we can calculate this number with a limit. Namely, simply this limit here. Or in other words, it's simply the same thing. And now this complex number we call the derivative of f at the point z0. And again, if you want to make it clear that we work with complex functions, you speak of the complex derivative of f at z0. So you see, the definition is not complicated at all, but please always keep in mind f prime of z0 is a complex number. Okay, then I think we are ready to look at two simple examples. The first one we consider should always be the linear polynomial, but now the complex valued one. So we have a function f where the domain U can be chosen as the whole complex plane C. And the definition of this complex function would be f of z is equal to a complex number m times z plus another complex number c. So this is simply the common linear polynomial, but now complex valued. There, because the function is already linear, a linear approximation will not change so much. However, let's try, for a given z0, to rewrite the function in this form. Hence first, we need f of z0, which is not so complicated because it's simply m times z0 plus c. And then we want to add z minus z0 times something. Now of course, this something we now can figure out. What we want to get in the end here is m times z plus c. The c we've already got, so we have to get rid of this term here. Of course, this is no problem for us because we can multiply this term by m. Then z0 times m will cancel out and the only thing that remains is z times m. Or in other words, now we have rewritten the function. The first term is f of z0 and this part here is our function delta. The function is constant, it's equal to m, so we don't have any problem putting z0 into it. Hence we know the derivative no matter which point z0 we choose. The derivative is always equal to m. This shouldn't be a surprise for you because the m stands for the slope of the linear function here. However, still, now we have proven that this function is indeed complex differentiable. And indeed, no matter which point z0 we consider. Okay, for the next part, let's look at an example where the function is not differentiable. Again, let's take the domain as the whole complex plane. And now the definition of the function should be that z is sent to the complex conjugate of z. So with our notation, we would write z bar. So you see, this is not a complicated function at all. To see what the function does, let's draw the input space here and the output space here. So our function f acts from the left hand side to the right hand side. Now let's take any point z from the domain, and then the function f just flips this point with respect to the x-axis. The real part of the number stays the same, but the imaginary part gets a different sign. So you see, this reflection is all the function f does. Therefore, it's not hard to show that this function is indeed a continuous function. However, it turns out that it is not differentiable, no matter at which point z0 we look. And this is immediately interesting, because in real analysis, it's not so simple to find such a strange function. Indeed, in complex analysis, this property is not strange at all. In order to see this, I would suggest that we try calculating the derivative at the point z0 is equal to 0. Indeed, all the other points will work exactly the same. Now, by definition, if the derivative exists, f prime of 0 is given by our limit. So we have f of z minus f of 0 divided by z minus 0. So we can immediately simplify this, because when we flip 0, we don't change anything. Hence, we have the limit z to 0 of z bar divided by z. Okay, and now it turns out that exactly this limit does not exist. In order to see this, please recall that z to 0 here means that in a complex plane, we have a lot of possibilities. So we can go from different directions into 0. For example, we could use the real number line to go from the right hand side into 0. For example, with the sequence Zn is equal to 1 over n. Hence, there the question is, what is Zn bar divided by Zn? Of course, this is not so hard to see. This is 1 over n divided by 1 over n. Or in other words, it does not depend on n, it's always the same number, 1. Therefore, also in the limit n to infinity, we get out 1. So the conclusion is, if this limit exists, it has to be 1. That this can't be 2, we see when we look at another direction. Now let's use the imaginary axis and run from the bottom to 0. For example, this can be done with the sequence Zn is equal to minus I divided by n. So again, we have the same question, what is Zn bar divided by Zn? So now, in the numerator, we actually have a flip. It's simply plus I divided by n divided by minus I divided by n. Therefore, we can cancel everything and the only thing that remains is the minus sign. So we get out minus 1. So we see, also in the limit n to infinity, this is minus 1. Which is of course not the same as before, so this is not equal. Therefore, the conclusion is the limit from before does not exist. In other words, f is not differentiable at the point that 0 is equal to 0. Accordingly, we immediately have a counterexample for differentiability. Here please recall, I already told you, you can do the same proof for every other point z0. So the conclusion is indeed the function is nowhere complex differentiable. At first, this might be surprising because the function is continuous and indeed a very simple function. In fact, we can reformulate this and say that differentiability for complex functions is a very strong property. And I can promise you this will get very apparent soon. And with this, I hope I see you in the next video. Bye!